Alrighty, guys, good morning, welcome back. I have a few kind of announcement-y things to start with before we get into the meat of the day. I guess I should wait for more folks to show up before I do any sort of announcement. So I'm just click on the document camera, put up the title card. MAC2311.0H1 This is California on, and it's November 22nd. 2021. The plan for today is to begin section 5.5, which is on integration via the substitution method. This is often just called U-sub, although I will sometimes use variables other than the letter U, for reasons that will become clear your very first week of Calc 2. Okay, we do have some more folks trickling in. Let's see, it's 11:02. I don't want anybody to miss the following announcements, but I also don't want to just waste class time sitting here waiting. So let me share with you. Oh yeah, I guess one other thing. I'm sorry, the videos for the last few classes. Videos for the last few classes are uploading now. Zoom updated last week, and that resulted in a change of the format, the outputs here. So the script that I have to like recognize and move these into a place where I can find them and label them instead of having a bizarre file name like this stopped working. So I had to spend some time and go back and figure that out. But I am uploading them now. They are there. If you look at the announcement from the 19th, that video is now linked. It's uploading and processing as we speak. It should be viewable by the end of class today. Okay. What I want to talk to you about today before we get started is something called the Jello. So you may remember from our syllabus, when we went over the syllabus at the start of the semester, one of the things we talked about was something called the General Education Learning Outcome, Jello. These used to be just a few questions on the final exam, right? This would be like 1 or 2 questions, 3, maybe 4 questions on the final exam that were meant to look and see, did you learn this very particular thing? The department has asked us to stop putting Jello questions on the final and to start assessing Jellos a different way, namely through some worksheets. So I know it's kind of the middle of the term, but I have to change things up just a little bit to comply with that new system. The General Education Learning Outcome, it's just a statistic that the state likes to track to see how the college is performing. It doesn't go on your transcript and it doesn't have anything to do with your grade in the class. What it's going to be this semester for us, instead of a few particular questions on the final, is this worksheet. It's a worksheet on Riemann sums, which I know is not anybody's favorite topic. But I went through they give us like 3 or 4 choices of things that we can use for Jellos. And this was the one that was the least crappy. So some of them are just really unpleasant. Others are less unpleasant. I'm going to be posting this worksheet in PDF form, hopefully a little bit prettier. I'm working on converting it to a tech document now, to Canvas. And I will need you guys to download, print, fill out, and then scan and upload this worksheet. It's just these 4 little questions. You're given the graph of a function f down here. And we want to approximate the value of the integral from 0 to 0.8 of f of x dx using this Riemann sum. They write this Riemann sum slightly different than we do in class, saying from I equals 1 to 4, f of x I minus 1. I want to make just a little note here that this is the same. Let me come over here. Oh, so Jello worksheet. Will be posted to Canvas today. This is mandatory. I need you to print, download, print, fill out, scan, and submit to the Canvas assignment. Jello, G-E-L-O, Jello, worksheet. So this is just in place of what used to be some questions on the final exam for the state to track how I'm doing as a teacher, to make sure you guys are getting the general education learning outcomes from this course that we would hope that you get from this course. This will be graded for completeness only. Not correctness. And I will give you 4 bonus points on your exam 2 score. For completing. All right, because the Jellos aren't meant to affect your grade in any direct way, like getting them wrong shouldn't hurt you. I'm not going to make the bonus points contingent on you getting the questions correct. I just need you to complete the assignment. It is very important that you don't get help, right? So don't look at your book, don't look at your notes, don't talk to each other, don't talk to a tutor. Make sure you do this worksheet 100% on your own, because it really is just about tracking how good a job I'm doing. It's got nothing to do with how well you're doing. It's got everything to do with how well I'm doing at teaching you these things. Unfortunately, this is prepared by a committee. So there is one bit of notation that is different than the notation we use. It's actually not different. It's just I wanted to show you. So this thing is all about Riemann sums. A quick comment on the notation.
But I have a question. How did you grade the score of this sheet?
So like I said, it's just for completeness. So you will, if you submit the thing, you're going to get all 4 bonus points. And then when it comes to assigning the Jello itself, I don't do that. These will get passed around to the rest of the department, and other professors will look at the work and decide whether that is a successful Jello or not. But your grade will just come from submitting the completed worksheet. So the sum that appears in there, the sum I equals 1 to 4 of f sub x I minus 1. This is a different notation for the left-hand Riemann sum than what we normally use. This is the same as the sum from 0 to 3 of f of x sub I. If you write this guy out, he is f of x sub 1 minus 1 plus f of x sub 2 minus 1, f of x sub 3 minus 1, plus f of x sub 4 minus 1. And 1 minus 1 is 0. So this is f of x sub 0. 2 minus 1 is 1. So this is f of x sub 1. 3 minus 1 is 2. So this is f of x sub 2. And 4 minus 1 is 3. So this is f of x sub 3. And that is genuinely the same thing as sigma and, or sorry, I from 0 to 4, f of x sub I. So I just wanted to show you that the notation they're using in that sheet slightly different than the notation that we've used, right? When we want to talk about the left-hand Riemann sum, we would do the sum from 0 to n minus 1. They do the sum from 1 to n, but then put an I minus 1 here. And these are the exact same thing. So the little sticking points here, I do need you to work this on your own. Don't worry about whether it's perfect or not, right? Just show me your genuine thoughts on it. You're going to get all 4 bonus points, whether the questions are correct or not, right? The correctness does not factor into what score I give you for this. You will get all 4 bonus points as long as you hand the thing in. The other sticking point here has to do with formatting. Because these are going to be passed around the department and graded by a bunch of different people, they all need to be formatted the same way, which means I can't have you like writing it out on notebook paper and then scanning that. In other words, I actually need you to print the thing. I need you to actually print out the document, fill it out on that sheet, then scan and submit. If you want to fill it out electronically, if you have like a tablet or an iPad, something like that, and you want to just draw on it digitally and then submit that, that's also fine. But I need it to be formatted exactly like the document I'm going to give you. So I can't, like writing it out on notebook paper and then taking a picture of that won't work. Like I said, I will try to get this kind of prettied up a little bit. I've started working on it, but I'm having some scaling issues with the graph for whatever reason. I'll show you here. So yours will actually look something like this, just with this graph less ugly. Well, that's it. So you're going to approximate the value of this integral using the indicated Riemann sum. You're going to describe how you would get better results, more accurate approximation. Then you're going to go ahead and do for part C, whatever it is you said you should do in part B. So, different method, more rectangle, whatever. And then in part D, you will interpret this in terms of the weather, because the function that we're talking about here is supposed to be measuring the rate of change for the temperature. So this connects to what we were talking about last time, right, with the net change theorem. And it also, of course, connects back to Riemann sums because you're doing a Riemann sum. And again, I just want to reiterate, please don't seek help from others on this. Just work it on your own. If you're genuinely not sure what to put down for something, you can write, I don't know. But do your best to think carefully about the problem and give me a good answer for each of those parts. I know you guys can do this stuff. But more than anything, I want to see an honest reflection of what goes through your mind when you're given a problem like this. All right, I'm going to put this assignment up in Canvas for you later today, and you can submit it anytime in like the next week. I think I'll put a due date of like the Thanksgiving, or not Thanksgiving, that's this week. I'll put a due date as like the last day of class or something. It won't take you more than 10 minutes. I promise it's a short assignment. But it is very important to the college. It's very important that you guys do those. If you don't do those, I get in trouble. So please, if for no other reason than for the bonus points and as a favor to me, please take the time to download this thing, print it out, fill it out, scan it, and then submit it to Canvas. If you do have any problems with it, you're having issues, don't hesitate to reach out to me, but please don't reach out to anybody else, because again, the statistics here are important for the state, and we don't want to see what the tutors say or what the book says. We want to see what you say. Okay, only announcement, that's it. Any questions about this thing? When does it due? I think I'll put the due date as like the last day of class, but the sooner you can get it in, the better. The department could call on me to present this stuff at a meeting. I don't think they would do that before the end of the term, but it would be nice to not have to worry. Okay, yeah, Tilly, I see your DM there. I haven't gotten through my emails just yet. I've got way too many of them. But I think I can probably meet tomorrow at 10. Yeah, I'll reply to that email later today. And if I don't have the time in my schedule tomorrow, we can probably do it Thursday. All right, so for anybody who just came in, the Jello worksheet is a little worksheet, this worksheet, that I am going to upload to Canvas for you. Actually, it's for you, it's going to look a little bit more like this. I'll fix that graph, but you're going to have the graph of a function. And you're going to be told that that function is the rate of change for temperature in degrees Fahrenheit as a function of the time, the number of hours since a thunderstorm began. So over here will be a graph for the rate of change of the temperature. What you're going to do is approximate the integral of that function, integral from 0 to 0.8, as a Riemann sum. And this is the left endpoint Riemann sum with 4 rectangles. So you're going to calculate that Riemann sum as an approximation to the integral. Then you're going to explain what we could do to get a better result, to get a better approximation. What could I do to make this Riemann sum closer to the actual value of the integral? We talked about that back in 5.1. How do we get better approximations? You can pick any method that you think will give you a better approximation. And then in part C, you're going to apply that method. So part A, calculate L4. Part B, talk about how to get better results. Part C, go ahead and do whatever it is you suggested in part B. And then part D, very last thing you're going to do is interpret the answer, which is the approximate value of that integral, in terms of the weather. So remember, this is a rate of change for temperature. So the integral of the rate of change is the net change. And that's what that's what we want you to do. So just download, print, fill out, scan, and submit that worksheet to Canvas as soon as you can. And I will give you 4 bonus points on your last midterm, on your exam 2 score. The Jello worksheet here doesn't have any bearing on your grade in the class. It's not anything like that. And I'm just grading these for completeness. You submit it with all the questions answered to the best of your ability, you're going to get all 4 bonus points. It's just something that the state and the college need in order to track the quality of our instruction. See whether we're teaching you guys the things we want you to learn. That's it. All right. So that's all of that stuff. I know it's kind of a pain, but we got to do what the department says. They say they want Jello's midterms as worksheets instead of on the final. I got to toe the line. Today, though, we're going to talk about integration by substitution, aka U sub. And this is section 5.5. What we're really learning here substitution is the backwards chain rule. So the chain rule, remember, chain rule for derivatives, in extreme brief, says d dx of f of u of x is equal to f primed of u of x times u primed of x. And so a backwards version of this, the substitution rule, says if you're going to integrate something like this, you should get something like this. Let me use the notation that your textbook uses, just to be careful. Yeah, we'll get there. All right, yeah, so they use, I'm going to use U instead of G, but yeah, they say the same thing we do here. All right. So the integral of f of u of x times u primed of x dx is the same as the integral of f of u du. That's basically what this says. And I know it might be hard to link this to this right away, but after I show you a few examples, kind of like the fundamental theorem of calculus, after we look at a few examples and recontextualize, I think you'll find it very straightforward. Before I can dive into like using this thing, what I want to show you is just a little bit the stuff that we're going to need to recall from previous sections, namely differentials. So sort of the game here is going to be, I give you something that looks like this, and you're going to make a little substitution to turn it into something that looks like this.
Is it at all like, there was some stuff in pre-calculus where we had to put a u in place of a number so that we could do certain math with it before substituting other stuff back in?
It's kind of similar in that we're going to be replacing a chunk of things by a single variable, and the label we're going to use most of the time will be the symbol u. But it is a different method than like trying to solve e to the 2x minus 3 e to the x plus 4 equals 0 by substituting u equals e to the x. It's slightly different, but kind of similar in spirit.
Okay, cool, thanks.
All right, so how might we solve the integral of 2x times the square root of 1 plus x squared dx? Sort of the unfortunate thing is that I've got a bunch of stuff underneath this square root. And square roots, say recall. First, the integral of a product of two functions is not equal to the product of their integrals. So we can't split this up as integral 2x dx times integral square root 1 plus x squared dx. Right? This is not equal to our problem, integral 2x times the square root of 1 plus x squared dx. And in fact, that's a good thing, because the second integral here is much, much harder than our whole problem. But one of the first things people are often tempted to do when they see something like this is to try and split it up. Say, okay, I'll integrate this and I'll integrate this, and then I'll just multiply those answers. That never works. And in general, the integral of a product is not the product of the integrals. Just like for derivatives, right? You need the product rule to differentiate a product of two functions. You would need the backwards product rule to integrate a product of two functions, unless you're doing something like u sub. That backwards product rule, by the way, is called integration by parts, and it's one of the first things you're going to learn in Calc 2. But we can't do this. I cannot split this integral up as the integral of 2x times the integral of 1 plus x squared, or square root of 1 plus x squared. Also, all of you made it through the skills test to get into this class. So hopefully we all remember that the square root of 1 plus x squared is not the same as the square root of 1 plus the square root of x squared. In other words, it's not 1 plus x. So I cannot say, oh, this thing is 1 plus x, and then try to distribute. That won't work. So neither of these kind of maybe first thoughts are kosher. Neither of these things are allowed. The second one is not true algebra-wise, right? Like plug in 1 for x. Here you'd have the square root of 2. Over here you would have 2 itself. And the square root of 2 is not equal to 2. Up here, this is a little bit more subtle, but the way to think of it is, well, if you can't differentiate products term-wise, you can't integrate products term-wise, because you need the product rule to differentiate products. You would need something like that to integrate products. What I can do is I can relabel the stuff underneath here as a new variable. What will work is changing the variables in my integral from x to u equals 1 plus x squared. Because when I do that, this piece is going to be u. So this big scary square root will just become the square root of u. And what we'll see is that this 2x and this dx interact with the new differential du. But doing this requires changing dx into du. So we need to talk about differentials. First. So I'm going to put this problem on the shelf for just a second. I'm going to go back and talk to you about differentials, what they are symbolically, what they are geometrically, and how we incorporate them into schemes like this. And then we'll come back and we'll actually make this little change of variables, and we'll see how that gives us an integral we know how to do. So there's going to be a bit of review today. Here's that review. In section 3.10, we learned that if y is equal to f of x, then dy is equal to f primed of x dx. The differential of y. And the way to think of this is that this tells you how y is changing compared to how x is changing. If x goes up by a tiny little bit, then y will go up by f primed times dx. So in other variables, in terms of variables u and x, if u is equal to u of x, then du is u primed of x times dx. So what we're going to be doing in our integral, remember, is changing the variables from x to u. What the du and dx do to each other is describe a scaling factor. It tells you how quickly the variable u is growing related to how quickly the variable x was growing. And in terms of areas, this has some serious implications. For example, so when working with integrals, the differential tells us how the horizontal axis scales compared to sorry, with the new variable u compared to the old variable x. So let me look at two very simple integrals. The integral from, say, 0 to 1 of 2x dx. Of course, we know how to do this integral. That's not terribly exciting. We could actually do this several ways. We could do this by interpreting in terms of areas and using geometry formulas. We could use this by do this by calculating an antiderivative and using FTC2. This is simple enough that we could also get there by taking the limit of a Riemann sum if we wanted. But I don't want to do any of that right now. I just want to compare this to what would happen if I make a little substitution. If I choose to relabel 2x as u, so here's my x-axis and here's my y-axis, then this would become the integral of u. So let me draw a graph down here. Instead of drawing y equals 2x, now I'll just draw y equals u. That's a line with slope 1 through the origin rather than a line with slope 2. So this is now the y-axis, and this is the u-axis. If I do this, then du is 2 dx, just taking differentials, right? The derivative of 2x is 2. So if u is 2x, then du is 2 dx. Question. What area here is going to be equal to the area here?
Half the size.
So if I was to just integrate from 0 to 1, this would not be the same as this, right? This is 1/2 times 1 times 2, right? This area here is just 1. If I were to look at the integral from 0 to 1 here, that would give me 1/2 times 1 times 1. So let me do a few things. Let me divide both sides by 2 here. And I see that dx is 1/2 du. So this becomes the integral of u times 1/2 du. Also, when x is equal to 0, my old bound's 0, so the lower bound 0. When x is equal to 0, u is equal to 2 times 0, which is also 0. So my new integral will start at 0. When x is equal to 1, u would be equal to, just plug 1 in here, 2 times 1, which is 2. So my new upper bound is going to be 2. So sort of what's the relationship between these two areas? This area and this area.
They're like a flipped version of each other.
Yeah, let me turn my camera back on here so I can make some hand motions. If I take the first graph, this one, and I stretch it out by a factor of 2, I'll get this one. Yeah, Talia nailed it in chat. This area is exactly twice as big as this area. Because this graph can be obtained from this graph by stretching it out by a factor of 2 horizontally. So when I transform the horizontal axis from the x-axis into the u-axis, every little step forward in x is twice as big a step forward in u. If you look at a small little dx change here, that will get stretched out to twice as long here. du is 2 dx. So this substitution, what it does, besides relabeling 2x as u, stretches the horizontal axis by a factor of 2. And you can see that when you look at the whole region, this region is twice as wide as this region. Right? This region had width 1. If I stretch that out by a factor of 2, I get this region, which has a width 2. But I haven't changed the height. The height here is still 2. So in order for these areas to be the same, I need to acknowledge that stretching factor that this substitution does. That's really what we mean when we say du is equal to 2 times dx. Means for every little step in x, u is going twice as far. In other words, when you make this substitution, we change our bounds down here, right? So that new integral runs from 0 to 2. And if you didn't include this 1/2, then this area is twice as big as this area. So to get them to be equal, we have to have that 1/2. In other words, you have to solve this for dx and tell me, what is dx equal to in terms of du? So when you make a little substitution like this in a definite or indefinite integral, but it's easier to see in definite integrals, when you make a little substitution like this, you're not just relabeling things. We are relabeling things, but this is the way this is very different than what you did in pre-calc, right? In pre-calc, when you went to solve some of those equations, you would relabel a chunk as u and then solve that equation and then plug back in. Here, when you do this, you're not just relabeling things. You're also stretching out the region. There's geometry involved because now there's calculus involved. You're stretching out that region. And what that means is you're going to change some of the geometric features of this space. Now, my goal is to evaluate this integral. I want to know, what is this? I'm going to get there by replacing 2x by u. That's fine. I can do that. But I need to make sure that I remember when I replace 2x by u, I'm stretching the whole picture horizontally by a factor of 2, which means I need to divide by 2 in order to conserve the area. So here's how these substitutions go. You pick what you're going to sub for. Then you calculate the differential du. You solve that differential for the old differential. My original integral had a dx in it. That was the differential here. In order to replace dx by its equivalent under du, you take this differential, which you calculate right after choosing your substitution, and you solve it for dx. That thing is what you plug in place of dx. This thing is dx. But now this is an integral that I could do. So these two integrals are equal. The integral from 0 to 1 of 2x dx is equal to the integral from 0 to 2 of u times 1/2 du. Now the truth is neither one of these are hard. You could have just done this guy, right? But I'm trying to get you to see why we're going to be doing what we do elsewhere. So let me go ahead and crunch out each integral to convince you that they are the same. And then we're going to return to that previous problem. Okay, so integral 0 to 1 of 2x dx, you can pop out the 2 and you have integral 0 to 1 of x dx, which is 2 times your antiderivative, x squared over 2 evaluated from 0 to 1. Which is 2 times 1/2 minus 0 over 2, which is 2 times 1/2, which is just 1. And the integral from 0 to 2 of u times 1/2 du, you can pop out the 1/2, integrate 0 to 2 u du. So we're now integrating u with respect to the variable u. So this is 1/2 times u squared over 2 evaluated from 0 to 2, which is 1/2 times 2 squared over 2 minus 0 over 2, which is 1/2 times 4 over 2 is also 2, which is 1. So these really are equal. But if I didn't have this 1/2 here, they wouldn't be equal. So when you make a u substitution in an integral, what you're doing is what's called a coordinate transform. You're changing the variables. You're coming up with a new coordinate system. And sometimes that can be a big help because you're also going to be relabeling things. Now in this problem, that relabeling doesn't make this integral any easier or any harder. But in many other problems, being able to relabel a bunch of terms as a single term really does make things easier. Makes finding an antiderivative easier. But because we're doing a coordinate transform, because we're changing the geometry of the space where this area exists, we need to compensate for any stretching or shrinking of the x-axis. So as I turn the x-axis into the u-axis on this problem, we stretched everything out by a factor of 2. More interesting problems have the stretching different amounts at different parts. So maybe it stretches out from 0 to 1, and then it shrinks things down from 1 to 2. Maybe it stretches out a little bit from 0 to 1, and a little more from 1 to 2, and a little more from 2 to 3. All of that will be characterized or described by the relationship between du and dx. So here the fact that du is just the constant 2 times dx means that this substitution stretches things out horizontally by a factor of 2. Okay. Let's return now to our original problem. We wanted to integrate, I think it was given as an indefinite integral, unfortunately. Yeah. We want to integrate 2x times the square root of 1 plus x squared dx. And the way we're going to do this is by relabeling the inside of the square root as u. We need to describe the relationship between du and dx. Well, we take the derivative over here. This is 0 plus 2x dx, i.e. du equals 2x dx. I like to put all the stuff for my substitution in a little box. So what this means is that when you make this change of variables, the x-axis gets stretched out not by a factor of 2, but by a factor of 2x. So from 0 to 1, it gets stretched out by a factor of 2-ish. From 1 to 2, it gets stretched out by a factor of 4-ish. If I draw here, I'll put 0 over here, 1 here, 2 here, 3 here. This is my x-axis. What this means is that my u-axis is going to be quite a bit longer. So 0 stays 0, 1 gets stretched out to 2, 2 gets stretched out to 4, all right, 2 times 2. 3 times 2 is 6, so this would be 4, 5, 6. All right, so we're stretching out the x-axis to get the u-axis. This is what's going on geometrically. You don't need to draw this when you do these things. This part's just for fun. What you do need to do is take this and solve. So u is 1 plus x squared, and du is 2x dx, which means 1 over 2x du is equal to dx. So my integral of 2x times the square root of 1 plus x squared dx. And this is why it's so important that you always write these differentials. This is equal to, I'll just plug in one bit at a time. This is 2x times the square root of u dx, which is 2x times the square root of u times 1 over 2x du. And this 2x cancels with this 1 over 2x. And you just get the integral of the square root of u du. And now this is an integral I know how to solve purely in terms of the variable u. This is u to the 1/2 du. And I apply my power rule. I get 1/2 plus 1 is 3/2. And if I divide by 3/2, that's the same as multiplying by 2/3. And we have a plus c coming in at this stage. And then finally, I plug back in the original variable. All right, this is an indefinite integral I'm trying to solve. I'm asking, what is the most general antiderivative of 2x times the square root of 1 plus x squared? That answer had better be a function of x. So this is 2 times 1 plus x squared to the 3/2 divided by 3 plus c. And that is the answer to this problem. The indefinite integral of 2x times the square root of 1 plus x squared is 2/3 times 1 plus x squared to the 3/2. Oh, and I just noticed something. So first, let's focus down here for a minute. Questions on this procedure. So like, here's the whole problem. Very important that we always write our differentials. Another thing that's very important, you cannot hope to get to your antiderivative step until everything is rewritten in terms of the new variable. So before we can integrate everything, double underline, must be in terms of the new variable. There cannot be any x stuff left over. In other words, I need this cancellation to be perfect. Technically, this object doesn't make any sense because it has both u's and x's and dx's in it. I cannot have a mixture of variables. Before I can even say the substitution is done, I need to get to this stage where I've only got u stuff and only have du, no x's, no dx's. Okay, real quick, the thing I noticed here, this picture is actually not correct. Let me retcon some of this. Put 8 over here, 7, 8. Du is how much we're stretching by. So du is 2x dx. So 2 would get stretched by a factor of 2 times 2, which means 2 is going to get sent all the way over here to 8. 2 gets stretched by a factor of 4. So this is what I mean when I say it stretches different parts of the line different amounts. The interval 0, 1 gets stretched to the interval 0, 2. The interval 1, 2 gets stretched to the interval 2 to 8. So sort of alternate colors here. This piece, the 0 to 1 piece gets stretched to the 0 to 2 piece. And then the 1 to 2 piece gets stretched all the way to the 2 to 8 piece down here. So we're stretching the x-axis by different amounts in different parts. Pretty cool, right? This 3 would get stretched by a factor of 2 times 3, which is 6. So this 3 would get stretched all the way out to 3 times 6 is 18. So if I wanted to show how far 2 to 3 gets stretched, I would need to have this go all the way out to 18. But this is just fun to think about. This is the procedure you need to get good at. So I want you to focus for now on this. Again, questions on any of what we did here or why or how. Okay. Let's look at some more examples. Suppose I want to integrate sine of 5x. Well, I know the antiderivative for sine, like sine of x, but I don't know the antiderivative for sine of 5x. So here, if I can substitute u equals 5x, then I'll be able to rewrite this as an integral just in terms of the sine of u, which is easy. I just need to remember that that means du is 5 dx. And solving this for dx, I get 1/5 du equals dx. So this would become the integral of sine of u times 1/5 du, because this is dx. And these u subs where the differential is constant, like here du is just 5 dx, those are easy because the constant will always then pop out. Leaving us with the integral we want. Antiderivative for sine u is negative cosine u. I'll write my plus c because it is an indefinite integral. And then finally, we simplify and we replace this variable by what it was originally. This is going to be negative 1/5 cosine of 5x plus. And you can check, just like Daniel was checking when he talked about indefinite integrals last Friday, that if you differentiate this by the chain rule, right? First, the negative 1/5 would just come along for the ride. And then by the chain rule, the derivative of cos 5x would be negative sine 5x times 5, and the 5s will cancel. Questions on this one? Okay, a little comment. Similarly, one can show that for any constant a, the integral of the sine of at, or say ax dx, is going to be negative 1 over a times cos ax plus c, and the integral of the cosine of ax dx would be positive 1 over a times the sine of ax plus c. Let's look at some harder problems. One of my favorites. Does anybody see a substitution here?
ln x is equal to u.
This is nice because of the differential. If u is equal to ln x, what is du?
1 over x dx.
Very good. And if I solve this for dx, I get x du equals dx. So the ln of x, that is just u. Downstairs I have an x, and this dx is x du. And the x's cancel. And I just get the integral of u du. Whose antiderivative would be u squared over 2 plus c. And then finally plugging back in, this would be the ln of x all squared over 2 plus c. All right. These can be a little bit tricky. Here's another one that I like a lot. My wife's Calc 2 teacher put this on the first test last spring. I thought that was fun. Does anybody see a substitution we could make here?
The x minus 1 under the radical.
Yeah, and just like that very first problem, here I want to substitute for the thing under the radical, because it's the radical that's making life hard. So if I let u be x minus 1, what is du?
One.
Yeah, the derivative of x minus 1 is just 1. So this would be 1 dx. In other words, du is equal to dx. So this will become the integral. Let's see, I don't know what to do with that x just yet. The square root of x minus 1 is the square root of u. Dx is the same as du, right? Here, du and dx were equal. And at this point, this looks like bad news. What's wrong with the integral I just wrote down?
You won't be able to cancel out the x's.
Yeah. Remember, everything has to be in terms of the new variable. Everything, double underline, in terms of a new variable. This x, this lingering x, is a problem. But it is a problem I can fix. Is there any way I could possibly rewrite x, this x, in terms of the new variable u?
U plus 1.
Yeah, very good. Since u is x minus 1, u plus 1 is x. We just go back and solve the substitution for the original variable. So this becomes the integral of u plus 1 times the square root of u du. And at this stage, you might ask, why did you even bother? How is this nicer than this? And I want you to think on that question for about 10 seconds. Why is the bottom integral nicer than the top integral?
Because it can write look like the sum of antiderivative.
Good, very good. So this is nicer because u plus 1 times the square root of u is equal to u times the square root of u plus the square root of u. I can distribute, which is u to the 3/2 plus u to the 1/2. And I can't distribute the original. Because remember, the square root of x plus 1 is not the square root of x plus 1. So I had some addition or subtraction going on underneath the square root in the original. And I don't have any way to kind of split that up. But by making the substitution, I moved the addition or subtraction from under the square root, now there's just a single term under the square root, to over here. And this isn't being raised to any weird power, so I can distribute that. And what I get is u to the 3/2 plus u to the 1/2 du. Please always write your differentials. Do not skip writing the du or the dx. I will take off points. Now I can calculate my antiderivative. 3/2 plus 1 is 5/2. So this is 2/5 u to the 5/2 plus 1/2 plus 1 is 3/2. So that's 2/3 u to the 3/2 plus c. So my integral is gone at this step. I took the antiderivative. That means the integral goes away. And I slap on my plus c. And then finally, because it is an indefinite integral, we do need to go back to our old variable. U was x minus 1. And I think we would all agree that it is not immediately obvious that this is the derivative of this. It's actually fairly complicated. Even just checking that when you differentiate this, you get this is a little tricky. But it is true, and you can check. Works out beautiful. So these are some basic U substitution problems. Before I let you go, I'm going to show you one slightly harder one. And then next time, we're going to focus on definite integrals. With definite integrals, things are a little different. You need to change your bounds when you make a substitution for those reasons I described to you earlier. But you don't need to go back to the original variable, which is nice. This is one of my favorite integrals. I have a book, by the way, called Garden of Integrals. There's several books on integration. And this is just one of those beautiful ones. Does anybody see a substitution we could try for here?
E to the x, maybe?
Very good. And in fact, before I even attempt that substitution, I'm going to use an algebra fact to make the substitution a little bit easier to see. E to the 2x is the same as e to the x squared. All right, that's how exponents work. A to the b, all to the c is a to the b times c. When you raise a power to a power, you multiply the powers. I think from here, it's pretty easy to see that we want to substitute u equals e to the x. And then du will be e to the x dx, because the derivative of e to the x is e to the x, which means that 1 over e to the x du is equal to dx. So that e to the x upstairs will cancel. I'll write it out. So this e to the x I'll rewrite as u, because he's kind of the thing that told me to make the substitution. And then dx is 1 over e to the x du. This whole thing is dx. And the e to the x's cancel. So I'm left with, by now you know, one of my favorite functions, or the derivative of one of my favorite functions, whose derivative is 1 over 1 plus u squared.
Tangent.
Tangent.
Good. Yeah, this is the inverse tangent of u plus c. And then because u is e to the x, this is the inverse tangent of e to the x plus c, like this. All right, this has been your introduction to U substitution. probably the single most important method you're going to learn for integration, certainly the most important one you're going to learn in Calc 1. In Calc 2, I will teach you integration by parts, trig sub, partial fractions, all sorts of good shit. But here, this is the most sophisticated method we're going to learn in Calc 1 for finding antiderivatives, for evaluating integrals. Next time, I will show you how to do this with definite integrals, which is mostly the same, but a little different. I'll warn you, if you've seen this before, like in high school, or if you've taken a Calc 1 somewhere else, or even watched videos, some people do substitution in definite integrals wrong. I'm going to just say it. If they don't change the bounds, they're doing it wrong. So tomorrow, when I'm going to show you how to do substitution in definite integrals, it is imperative that you rewrite anything in your brain if you have something in there already. Because yeah, we're going to do it right. That's it. That's all I have for you guys today. I'll post a homework assignment for you in a few moments with some problems to work on. The first half will be indefinite integrals like this. Then there will be some definite integrals. You don't need to work on those until after class on Wednesday. And then, yeah, Sarah, we are getting close to your student teaching. I would love to meet with you. Tomorrow at 10, I'm planning to meet with is it Talia? So I think that's the only block of time I have open tomorrow, but maybe Thursday morning we could meet, or if you're available for any of my office hours, Monday, Wednesday, Friday, how's your schedule looking? Oh, that's right. Thursday and Friday are holidays. I'm sorry. No, you're right. I can't. I'm going to be out of town too. Give me just one
Yeah, I
more.
figured it'll be chaos.
So, Talia, we have a meeting. You wanted to meet tomorrow morning at 10, right, Talia? Is she still here? So I have this available on me. Looks like she might have left. Okay. Tell you what I'll do. I will go ahead and schedule for both of you guys tomorrow at 10 a.m. And it's going to be a 1-hour meeting, and we will try to make that work. If we're unable to get through both things, then we can find, we'll force it in somewhere else. If we have to do it like late in the evening, or worst case scenario, like over the weekend or something, we can do that too.
Late in the evening actually works better for me for tomorrow than 10, if that's possible.
Unfortunately,
there's like
it
a
doesn't work
small
especially
chunk.
well for me. I would normally be okay
Okay.
with that, but my wife has classes at night, so I'm on baby duty in the evening. So ideally, we would do earlier. But I will go ahead and send this link to both you and Talia. If you can't make it tomorrow morning, just let me know, and we'll find a way to make it happen either in the evening or on a different day.
Okay. Yeah, I was just hoping that, because tomorrow afternoon I'm hoping to prepare some more of the materials. I have like a basic outline, but there's just some more materials that I wanted to be able to show you before I do the actual student teaching, and they won't be ready by 10 tomorrow.
Okay, I understand. If we can chat a little bit tomorrow morning, that would be nice. If we can't, then we'll find a time either tomorrow evening or something like that where we can chat and go over materials.
Sounds good. In the meantime, whatever I have done by the end of today, as far as like outline and such, I'll just email it to you.
That sounds good. I'll take a look at that and let you know if there's anything we need to change or anything I'd like you to add or anything like that.
Okay, perfect. Thank you.
Alrighty, guys.
Excuse me, what chapter will I learn on Wednesday?
We will do more of this. We'll stay in section 5.5, but we'll be talking about definite.
Okay.
Mr. Vilsaker, massive favor. I just realized that I forgot to do the homework that was due today. I was wondering if you could extend it to 11 p.m.
Of course, yeah, go ahead and submit an extension request in WebAssign. I think I have like 44 of them waiting for me now. So go ahead and drop one in there and I will get those all cleared out before my office hour starts.
Alrighty, thank you so much.
Yeah, no big deal, no big deal. Anything else I can do for you guys? Alrighty, then I'm gonna go ahead and end the meeting here. I'll see you guys on Wednesday. Take care.